So hello everybody. Today again we are going to discuss about fluid, and so it's lecture number 2 in continuous with the previous lecture. So now let's start. So for the today the topic is fluid as a continuum. Okay. So what that means we will learn it in the upcoming session. Okay. So from the previous lecture, we can say that fluids are aggregation of molecules widely spaced for gas, and for liquid it is closely spaced. Okay, so what I mean to say is, if fluid is there, it can be divided into gas and liquid. Okay, which was discussed in the previous lecture. Okay, so for the gas, the molecules are widely spread. Okay, and for liquid they are closely spaced. Okay, I mean this white round things are the particles. Okay, or the molecules of fluids. Okay, so widely spaced for gas and closely spaced for a liquid. Okay, and one more thing that we have to notice, like if a molecule is there, and let's suppose the diameter of the molecules is d. Okay, and the mean free path of this molecule is very large as compared to the dimension of this molecule. I mean diameter of the molecule. So as you all know that I guess you have all studied in your class school days. So like this is the molecule with diameter d. So it should do some random motion here and there, like a zigzag motion or anything. So so there is one term known as mean free path. Okay, so mean free path means when a molecule start moving and it will collide with some other molecules for sure, because the space is limited. Okay, so that's why it will collide somewhere. So the distance that traveled by these molecules between two successive collision is known as mean free path. Okay, and for these fluid particles, I mean these fluid molecules, the mean free path is very larger as compared to the molecule diameter. Okay, so this means that. Okay, and the another point that we have to make note of that is the molecules are not fixed in a lattice but move about freely related to each other. As I have told here, like molecules is not fixed here. Okay, I mean they are doing random motion here and there in both the cases. Okay, in both in liquid and gaseous. So as we have discussed initially, like term like fluid pressure, fluid density, everything. Okay, so since the molecules are in the motion, as they are not in the static state, so the fluid density or mass per unit volume has no precise meaning. Okay, as the number of let's suppose we have considered unit volume kind of something. Okay, so as the molecules are in the motion, that means the number of molecules in this is not constant in the box. Okay, so for this region, the density for this region, okay, exactly for this region, density, pressure or anything is not constant. Okay, it will not be constant because the number of molecules kept changing, which means the density and the pressure and the volume of the this box will keep changing. Okay, so so how we are going to define the density, pressure and everything in the fluid region. Okay, so the catch is here, like we will decide a volume such that we will define a volume such that it should not be much larger and it should not be much smaller. Okay, not very large and not very small. Okay, so in that case, let's suppose we have selected a volume where I mean 50 molecules are there. N is 50. Okay, so even though some molecules, like 2 to 5 molecules kept coming and going from this box, even though the density and pressure will not change, will not vary that much. Okay, because as compared to 50 particles, the two number of particles which is coming and going, I mean which is not constant, is very insignificant. Okay, so we can say that nearly the number of particles in this box is almost constant. Okay, almost constant. Okay, so we have to select that much volume. Okay, so that that the volume is not so much large and not so much small. Okay, so if the volume now the question come in your mind, like why it should not be very small. If the volume is too small, that means the number of particles it will be there is 10, and if we remove about 2 to 3 particles from that box, there we will see a significant changes. Okay, in both density and pressure. Okay, so that's why we can't say we can't choose a very small volume. And even though if the chosen unit volume is too large, there could be a noticeable variation in the bulk aggregation of the particles. Okay, let's suppose if we take 500 particles in the box, that means box is much larger, so the number of particles which will come and go will be larger as well. So let's suppose 100 particles, I mean 100 particles will come and go in that box. That means that 100 particles is too much significance to calculate density and the pressure in our control volume. Okay, so we have to select such a volume that the effect of particles motion will be negligible. Okay, so how we will select that volume is like, see, we will define a density like limit delta V is delta V star. Okay, and delta M by delta V. Okay, so that means we have defined a density where the volume is tending to delta V star. So this delta V star, sorry, this delta V star is known as limiting volume. Okay, limiting volume. Okay, so at this volume our this approximation works at best. Okay, I mean this control volume that we have assumed is works at best, means the effect is negligible here. Okay, the best volume that works here. Okay, and then the question come in your mind, like how much it would be for any fluid and any particle. Okay, so for all liquid it is about almost delta V is almost equal to delta V star, I mean is equal to 10 to the power minus 9 millimeter cube. Okay, it should be the limiting volume for all the fluids and for gases at the atmospheric pressure. Okay, okay, and another thing that at this volume 10 to the power minus 9 millimeter cube, the number of particles would be there is approximately 3 into 10 to the power 7 molecules. Okay, that's all our experimental value. Okay, I'm just writing these values so that you can the things become clear in your mind. Okay, okay, and one more thing is that one more point that we can improve from these values, like see, limiting value is coming as 10 to the power minus 9 meter cube. Okay, and if we see all our physical dimension in this world, or if we what the dimension that we are going to deal in this topic is much larger than this what to say limiting volume. Okay, the physical dimension is much larger. Okay, okay, and so this method is known as continuum physics, continuum fluid. In overall term this is known as continuum physics. Okay, so continuum fluid. Okay, that means we are considering the fluid as a packet kind of things. Okay, packet kind of things where where we are defining that density and pressure, everything, and that remains constant. Okay, remains constant. So this is known, this process of dealing with this fluid is known as continuum fluid. Okay, so for the whole topic we are dealing with the continuum fluid. Okay, okay, so now we are going to discuss a new topic that is known as dimensions and unit. Okay, so this topic is not so much important as a physics of fluid. However, there are some important points that I want to make a note of it, so that there is no confusion will be there in the future part of the topic. Okay, so first one is, what is dimension? Okay, so dimension is the measure by which a physical variable is expressed quantitatively. Okay, so like what that means, I will explain it shortly. Okay, here, so suppose someone says someone had applied a force on me. Okay, so that person says that someone has applied force on it, so you don't know how much force it is. Okay, so dimension is that it will express quantitatively, like how much force have you applied, have you been applied. So that person will say like 5 Newton or something. Okay, so this quantitativeness will be done through the dimension. Okay, the Newton is the dimension of it. Okay, and what's the unit? Unit is the particular way of attaching a number to the quantitative dimension. Okay, so like say someone say 5 forces, you are not able to understand like 5 forces means what, 5 kilonewton, 5 mega newton, 5 newton, anything. Okay, so the unit will describe it completely. Okay, whether the force will be 5 Newton or 5 kilonewton. Okay, and the third point is dimensional analysis. Okay, so it's dimensional analysis. Okay, so what's the dimensional analysis means, I just want to say is like, we will understand in the upcoming points. Okay, so this dimensional analysis is very much important, like most of the correlations have been developed through these only. Okay, and in the future one chapter I will dedicate over this topic, dimensional analysis. Okay, so first we will learn 4 primary dimensions. Okay, what are the 4 primary dimensions? The primary dimension is mass, length, time and temperature. So there are not only 4 primary dimensions, these are valid for our course. Okay, so in our course we will mainly use only this 4 primary dimension. However, in some cases like some electric field is given or everything, then we will attach another dimension, that is current, and that is ampere. Okay, so I don't think we will going to use that current, but this 4 primary dimension is very useful in our courses. Okay, and the next point is principle of dimensional homogeneity. Okay, what that means is, let me explain with this example. I have written p plus 1/2 rho b square plus rho gh. So what is this? This is Bernoulli's equation. Okay, Bernoulli's equation. Okay, so what that principle of dimensional homogeneity says? It says that, like, see, in each additional term, each term in the addition will have the same dimension. For example, pressure having dimension Pascal. Okay, if we see this part, half dimension of rho is mass by volume, that means kg divided by meter cube. And what's the dimension of velocity? Is meter per second. However, it is the square term, so we will make it meter square per second square. Okay, now meter cube will cancel out here. Okay, so what is this? Half kg per meter square. Okay, now we know that if we multiply mass above and mass mass above and mass in the volume, in the length above and length in the bottom, we will get remove it half. This is not meter per second square divided by 1 by meter square. Okay, what is this? This is Newton, and Newton divided by mm square is Pascal. Okay, so the overall unit of this term is Pascal as well. And if we see in this case here as well, we will see like, see, kg per meter cube, meter per second square into it is meter. Okay, so meter square, so kg meter 1 per second square. Okay, if again multiply meter above, meter above, we will get kg meter per second square 1 by meter square. This again comes Pascal. So what I meant to say is, principle of dimensional homogeneity says that in each term where we did the addition, the dimension of each additional term is same. Okay, that means this is the first term, this is the second term, this is the third term, and the dimension of all of them are equal. So this is known as principle of dimensional homogeneity. Okay, so from this as well, we can in future we can prefer we can infer much more important thing from this. Okay, so till now it's just enough to understand the concept of principle of dimensional homogeneity. Okay, now another topic comes is homogeneous versus dimensional inconsistent equations. Okay, so I have written one example. So this example is of a, a formula that pipe valve manufacturers cited for liquid volume flow rate. Okay, so this is flow rate. That means the dimension of this is something called meter cube per second. Okay, and if we see SG means specific gravity. Okay, liquid by liquid density of water, so it is unitless, and delta P having dimension of Pascal. Okay, so EBC, and this is, sorry, CB is known as discharge coefficient. Okay, discharge coefficient. But if we match both LHS and RHS, we are getting that the dimension on the LHS is meter cube per second, and the same dimension would be there in the right hand side, but we are getting the Pascal and half n to CB. Okay, so we don't know the dimension of CB because it's a what to say, coefficient. So we will describe the CB as dimension meter cube per second divided by Pascal to the power half. Okay, so this we can calculate the dimension of CB. So initially when they are computing this formula, they are not aware of the dimension of the CB. Okay, so they are just putting a dimensional coefficient. Okay, and from this inconsistency in between left hand side and right hand side, they come to know that the dimension of CB will be like that. Okay, so this is the another tool that we can use and find out the dimension of various other things. Okay, so this is for this is done for this lecture, and we, in the upcoming lectures we will discuss the properties of the velocity field, and we will also see how the Euclidean and Lagrangian field are different. Okay, so till then, goodbye, and